And that's the secret to organic chemistry. All right, so like I said, one of the things in here that I think gets a lot of people is just how much is going on. And Orgo 1 is in large measure a language class. Okay, all of you have probably had a language class at some point. So I've written something here. I don't know if it means anything to you right now or not. But a lot of whether or not you succeed in organic chemistry comes down to how fast something like that does mean something to you, right? So if you think about language, if you're a native English speaker, you don't really do, your brain is doing a tremendous amount of activity when you hear me talk. But you guys don't hear me talk and translate every word, right? It all generates an image in your mind. You know, if I say camera, you don't have to do much to picture a camera. But if you hear a word in a camera is a bad example, right? Camera's camera in a lot of languages. But you know, if I say boligrafo and you know some Spanish, you have to jump through a couple of hoops. You have to turn that into an English word that generates the image in your mind, unless you're super fluent in that language. So that's going to be the case here. The first third of this class is really sort of the language of organic chemistry, how we symbolize molecules on a piece of paper or on a board, so that we can talk about it. If you don't get that really well, it's like jumping into Spanish 200 something if you really haven't had any Spanish. Right? It doesn't matter how smart you are, if you don't know what the words in the literature mean, you can't talk about the literature. All right, so make sure you get the beginning down best you can. Let me draw something on the board now. So, what is that?
Water.
That's water. Everybody agree that that's water? This is what I mean about language. First of all, yeah, you're right. Second of all, you're wrong. That is not water. That's why that works. That's water. Right? You guys have lived with this, you know this. Water is a physical substance. This is a symbol of water. And this is what I mean by language. I've written something that makes you think about water. And when you think about water, hopefully, so this is also a big part of this class, don't forget the simple stuff that you already know. Right? You guys know what water is. You know that it boils, it's really hot when it boils. You can burn yourself with boiling water. You've encountered frozen water, solid water. You saw some this morning. If you got up early enough. Or stayed up. Did anybody actually physically see it snow today? Anyone? Cool, good. I just sat down. Thank you. All right, so what we're doing in this class is we're coming up with ways to picture the molecules of water. Anybody got a guess as to how many molecules of water are in this? It's on the camera. More than 100? Less than 10 to the 50th? So how many, let's do some Gen Chem. See if you can do this in your head. First of all, there's not going to be a lot of quantitative mathematics in this class. All right? Organic chemistry and general chemistry, so you've just come out of general chemistry, you solve all these problems where you got to come up with a number, right? Where you have to solve equations. There's almost none of that in this class. So this class is very much not, it's chemistry, it's very related to general chemistry. There are a few foundational things out of Gen Chem you need to know, but on the other hand, it's very different. It's a lot, the analogy I like is organic chemistry relates to general chemistry the way geometry relates to algebra. Right? There's certain logical flows that are consistent between the subjects, but they look really different on the page. And it's possible to be good at geometry and love geometry and not be good at or hate algebra. It's also obviously you can flip that. You can love and be good at both of them. You can hate both of them. Okay, so how many molecules of water? I'll keep it on camera. So to figure out how many molecules there are, right, in that little bit of water, you'd have to know how many moles there are. So what is the volume of a mole of water? And is that a fair thing to ask someone to do in their head? You can also write it down. Yeah.
I'm probably wrong, but is it just oxygen, which is 16 on the atomic mass, and then two hydrogen?
So what's the molecular weight of water?
17.
How many hydrogens?
Wait. Two. Wait.
So
Yes, but I look at it, 16 plus 2 is 18.
yes.
I do that.
No, that's organic chemistry. 17, 18. No, it's 18, right? So the molecular weight of water is oxygen 16 plus 2 hydrogens. So you were doing it right. 16 plus 2 is 18. So 18 grams per mole. That's the molecular weight. So 18 grams of water is 6 something times 10 to the 23rd mole, or molecules. Right? That's a lot of molecules. So what's the volume of 18 grams of water?
18 centimeters cubed.
What's another way to say centimeters cubed?
Milliliters.
Yeah, 18 milliliters. So again, in general, and again, this also highlights a difference between organic and general chemistry. So technically, the density of water is not 1 gram per mil or centimeter cubed. It is going to be something like 1.00045 or something, and it varies with temperature, right? And so ice is less dense than liquid water, so it floats. The density of water also changes from 0 to 100. In organic chemistry, we hardly ever, I shouldn't say ever, especially since I'm being recorded, we tend not to deal with anything right at the decimal point, all right? The density of water to an organic chemist is 1 gram per mil. 0 degrees, 4 degrees, 88 degrees, whatever. 1 gram per mil. So 18 grams is 18 mils. This is, if I'd done this in a beaker, you might be able to get that. That's going to be about 250 mils. Let's call it, actually, let's make it easy. That's 360 mils, I'll say. Right? So that's going to be 20 moles of water. So 20 times 6 is 120. 120 times 10 to the 23rd molecules. All right? So to an organic chemist, what you would say is there are a lot of molecules of water here. All right? A whole bunch of molecules. And that's what water is. Drawing water this way lets us talk about one molecule. And then you can see the chemical structure of that. So this oxygen has a couple of lone pairs. The hydrogen has one bond. The oxygen has two bonds. You all basically either shook your head or said out loud water when I drew that structure. So keep water in mind. Any molecule that's got oxygen in it, oxygen's going to have a neutral oxygen is going to have two bonds, two lone pairs. A neutral hydrogen is going to have one bond throughout all the different molecules we draw. You also end up getting so water is actually pretty magical. Water interacts with other waters really strongly, more strongly than most molecules interact with other molecules of themselves. Right? So you've seen the hydrogen bond. The hydrogen bond is not a covalent bond. It forms transiently. So, I mean, that looks like a pretty calm glass of water sitting over there. But if you could put like a GoPro on any given oxygen, you would see hydrogen bonds form and break a few 100 million times a second. Right? So the water molecules stick together more than most other molecules, but they don't stick together permanently. So hydrogen bond forms and a hydrogen bond breaks. Obviously there are more hydrogens on that oxygen hydrogen bond somewhere, that hydrogen. It's really dynamic. It doesn't seem like it because on average, it all evens out. The other thing is, you never have 2 molecules of water. All right, we just established that's like 10 to the 25th molecules, give or take. All right, a whole bunch of molecules. You might see a chemical reaction. Well, you will see a chemical reaction. This semester. So if we add HCl, hydrochloric acid, to water, a proton moves from the HCl to the water, to the oxygen. We get H3O plus and chloride. Right. When you see this chemical reaction, this does not mean, it does, stoichiometrically, 1 molecule of water reacts with 1 molecule of HCl to give 1 molecule of H3O plus and 1 chloride atom. But you would never do a reaction with 1 molecule. Okay, so if I write this, I've got a whole bunch of H2O, I've got a whole bunch of HCl. They react in a 1-to-1 fashion, but I always have a lot. When I sat where you sit 30 years ago, kind of the smallest amount of substance that we could, really work with would be like a nanomole. So 10 to the minus 9 moles. If you multiply 10 to the 23rd by 10 to the minus 9, you still have a very large number, right? That is still a lot of molecules. Now, today, we can kind of work with picomoles, femtomoles. So we've come down. Humans still can't really do a lot of stuff practically with 1 molecule. We can image 1 molecule, and that's pretty revolutionary. But we can't do a chemical reaction with 1 molecule. So it's always going to be this large set of molecules. So anytime you see me write things like this, remember, I'm not writing 1 molecule of this, 1 molecule of that. Saying if I take a whole bunch of one, a whole bunch of the other, they react together in a ratio, but there's a bunch of them. What that means, when we get our H3O plus and Cl minus, both of these are still going to be interacting with HCl and water that's in the solution. Okay, so in the language, you always have excess. Right? There's always more than one. So if it turned out that water could react with water, then it would. And you guys know it does, right? H2O reacts with H2O to give H3O plus and hydroxide. It's the equilibrium favors the 2 water molecules, but it's always there in the background a little bit. Questions about this so far? Like I said, I really want you to remember, you don't have to go through it all every time. But as we talk about substances, we're always talking about, we're symbolizing the real thing. Right? All of this is a means to an end to be able to predict the behavior of substances. So you're all enrolled in 122 lab, or you've taken 122 lab. Up there, you'll actually manipulate substances. Right? So the molecules I draw on the board are just symbols. The substance themselves are the real thing. What we want to do, in as much as possible, we want to be able to predict the behavior and the properties of a molecule based on its molecular structure, the theory that we have. The better we are at that, the better we're able to, figure out what you got to put in with some RNA to make it a vaccine. Or the better you can say, if I mix these 2 molecules, I'll get this new molecule that might be a drug. Right? That's what we're going for. And we have, like I said, over the last 2-3 centuries, humans have made tremendous strides in being able to do that. So 300 years ago, chemistry wasn't even really a science. The alchemists still held sway. They had tremendous practical knowledge. They had very little theoretical chemical knowledge, but they were better, probably practical chemists than a lot of us today. Right? You had people that could go dig in the dirt, pull stuff out, build swords and houses and stuff out of it. I am a pretty good chemist. I can't do that. Right? I have theoretical knowledge for how we do this, but I have no, if the apocalypse came and I had to make bricks, I can't do it. Hopefully I can figure it out. I guess I'd probably try to feed myself before I made bricks. Okay. Other thing, you all in the front row need to keep an eye on this. Let me know. It only goes 30 minutes. So when I upload class videos, they'll come in, I'll try to number them 1, 2, and 3, but there will be more than that. All right, so symbols, there's water, you've seen that. Oh, I was going to say, like I said, focus on the atoms, oxygen and hydrogen, nitrogen and carbon, and the halides. You basically need to be able to glance at them and know what their charge is and what their geometry is. We're gonna go over it. You don't have to do it just now. I'm just telling you where you need to be able to get. All right. So let's look at this molecule I've drawn over here. So take a second and come up with the empirical formula for that molecule. All right, so that's what I get. C4H8NO. Right? Molecular formula is just the atoms there. There are a lot of different, so C4H8NO is going to cover a lot of molecules. It doesn't really, the molecular formula alone is not going to really tell you a lot about the structure or the properties. There's a lot of different ways to arrange those atoms that will change their properties. Let's try to draw this out. I'm going to draw what I would call a bond line formula. I think this is chapter 2. And this is going to take advantage, the bond line formalism takes advantage of the fact that, at least in the second row and above of the periodic table, atoms have a very few different ways to make bonds. Okay, so carbon, anybody know offhand how many bonds carbon makes? 4, good. All right, so 1, I want you to know that. Carbon makes 4 bonds. But here's the thing. Carbon doesn't only make 4 bonds. Carbon makes 4 bonds when the carbon is neutral and in a stable neutral molecule, or a stable molecule. We're going to see during this semester, we'll see instances where carbon makes 3 bonds. We won't see carbon making 5 bonds. And for all intents and purposes, okay, this is one of those things where I have to, knowing a lot more chemistry than you, I feel uncomfortable saying carbon never makes 5 bonds. Carbon never makes 5 full bonds. Carbon can't have more than 8 electrons. None of the atoms in the second row can have more than 8 electrons. All right, but they can be 5 coordinate. It's rare and it's interesting. Right now, where you are, you should stick in your head that carbon will never have more than 4 bonds. And a carbon with 4 bonds will not have any more electrons. Okay, so it's going to be 4 bonds. Carbon can have 3 bonds, though. Carbon can have 3 bonds and no more electrons. It can have 3 bonds and 1 electron. It can have 3 bonds and 2 more electrons. When that happens, that means that carbon is going to be reactive. So by the end of this course, we're going to be talking about chemical reactions. A plus B goes to C, like we've got over on the board. All right. For a carbon to react, that means a bond has to break and a bond has to form. And that doesn't just happen, right? The carbon's not magic. It doesn't wave its hands and a bond switches out. The bond has to break either before or at the same time as a new bond forms. The new bond has to form either after or at the same time as an old bond breaks. Okay, so stable carbon, 4 bonds. And if you're going to talk about a molecule like this, this is probably going to be stable. And so we're going to assume that a carbon has 4 bonds. The same argument holds that hydrogen is going to make 1 bond, oxygen is going to make 2 bonds, nitrogen is going to make 3 bonds. And that lets us draw this bond line. Let me draw this in here. I can't draw molecules like this. This is what I was trying to draw. Because I've technically got a pentavalent carbon in here. I only proofed my notes like 3 times before coming to class. So here's the thing about language. This is a way to draw molecules. I never, after today, you'll never see me draw a molecule this way again. All right, so I'm trying to do this down here. And then obviously this is now going to change our molecular formula. And I should have known it. All right, 6, 7, 8, 9. C5H9NO. If there's a nitrogen in a molecule, it's going to usually have an odd number of hydrogens. I know that rule. I should have got it. All right. Here's what I'm trying to draw. All right. This is a bond line, and I'm going to go through the bond line and what it means. So in the bond line, everywhere that the line ends or there's an intersection is a carbon. Okay, so this carbon, the end of the line is a carbon, that's a carbon. 3 lines coming together here, that's a carbon. There is a carbon. You got lines coming together here, that's a carbon. All right, so it's organic chemistry. The class is organic chemistry. So we do not have, it's about molecules that have carbon in them. So we're going to focus on the carbons. And we're going to assume, if we don't write an atomic symbol in, that the atom is a carbon. All right, and now, you guys all just told me, carbon has 4 bonds. So we are going to assume the carbon has 4 bonds. So here's a carbon. Right? If I write that C there, now I don't just assume what it's bonded to. I'm just writing that C to write a C in. How many bonds does that carbon have? How many bonds is it shown? 1. Yeah, it's an easy question. All right? If I'm showing 1 bond to the carbon, that means the other bonds are to H's. Right? If I don't show any other bonds, those bonds are to H. Right? And we would call that a methyl group. So you're going to need to learn the names of the simple hydrocarbons. And again, this is chapter 3. We'll go over this again. But methane, which you've all heard of, right? Everybody's heard of methane. CH4, simplest carbon hydrocarbon. 4 bonds to the carbon. So if CH4 is methane, if we pull 1 hydrogen off and we make that carbon bond to something else, that CH3 group is called a methyl. So for example, if we have a CH3 bonded to an OH, that's methyl alcohol, or methanol. The alcohol is called a functional group. And the reason is you can sort of categorize chemical reactivity and behavior and structure and properties by the functional group. It's a group that functions. So if you have an OH, all OHs are kind of going to do the same thing. And we just had that up here, right? H2O is kind of like H bonded to OH. The OH hydrogen bonds has a higher boiling point than you'd expect for its molecular weight. And so methanol also will hydrogen bond to each other. Has a pretty high boiling point. The next one then, the next hydrocarbon has two carbons, is called ethane. I think everybody knows this one. So if you take a hydrogen off of ethane and you put the CH3, CH2 group onto something, it's known as an ethyl group. And if you do that to an alcohol, to an OH, you get ethyl alcohol. All right, everybody's familiar with ethyl alcohol. So again, those are both alcohols. The functional group's the same. They have an OH bonded to an sp3 carbon. More on hybridization in a minute. So ethanol and methanol have a lot of similarities. And again, the OH, they have similarities to water. They hydrogen bond really well. They boil higher than you would expect based on their molecular weight. They're relatively polar. But they also have differences. Okay? So you can drink water. In fact, you have to drink water. You die if you don't drink water. You can drink ethanol. So ethanol and methanol are both poisons. Anybody disagree? All right. Methanol is a way worse poison than ethanol. Lots of things are poisonous. Lots of things are bad for you. The dose is usually the important thing. Drinking just a little bit of methanol is going to be very bad for you. All right, your body responds to alcohol, drinking alcohols by oxidizing them. So you've got, depending on who you are and your genetic background, you've got different amounts of alcohol dehydrogenase in you. When you drink ethanol, your body goes to work, starts oxidizing that ethanol up to acetic acid. Acetate is you get a little bit of nutritional value by drinking ethanol. It's not an excuse. All right, so you can drink some ethanol, you oxidize up to acetaldehyde, and then on up to acetic acid, and you excrete the acetate. Methanol, alcohol dehydrogenase does exactly the same. Alcohol dehydrogenase does exactly the same thing to methanol. It oxidizes the methanol to formaldehyde, and ultimately it would oxidize it to formic acid and you would excrete it. Formaldehyde is really toxic. All right? So drinking methanol can kill you. It can make you go blind because your eyes are sensitive. This is good for lab. Your eyes are one of the most sensitive, vulnerable parts of your body. All right? And so there are all these protections that have been built up for your eyes. I mean, it's really extraordinary that we're able to have these two very fragile things just sort of out in the open. They're absolutely important for us, and they're really easy to tear up. So wear your lab goggles, and don't drink methanol. See, normally you'd see me smiling, and that would be funny. That's a sign that I'm meaning it. Don't drink methanol. It's not a joke, but I don't think most of you are going to. Ethanol